In the previous video, we defined the quadratic variation for a square integrable martingale, and we agreed there are two ways to understand it. So one way is to square out, so through the Doob decomposition, so to square our martingale, to split it into the martingale part and the increasing part, and that increasing part is the quadratic variation. The second approach is to use this formula, which looks very much like what we would call quadratic variation. And also we have this third formula, but these two are really one step away from each other. So the only reason why I'm making difference here is because it will be more convenient to use one of them in one scenario and the other one in the other scenario, and I will want us to see both of them at the same time. But those two are basically the same. So today we are going to see three examples of martingales and what their quadratic variation is. So the most obvious martingale that we know is the random walk. I will compute its quadratic variation using both methods, just so that we can see how they work. So the first method tells me square your martingale. Its value at time 0 is 0, so that's not a problem. But now split it into a martingale and whatever is left. And here we are just lucky because in some previous videos we proved that this process is a martingale. So this is a martingale. And then whatever is left is n, as simple as that, not even random. And this is then, by definition, the quadratic variation of S at time n. And by the way, the quadratic variation of the Brownian motion at time t is simply equal to t, and this is perhaps not surprising given how closely related Brownian motion and random walk are. Okay, now second way of computing the quadratic variation for the random walk is taking one of these formulas, and here I prefer to take this one because it works with the increments, and the increments of the random walk are very nice. They are these steps here. So here I will say, okay, Sn is equal to the sum from 1 to n, the conditional expectation of my ith increment will be epsilon I squared f I minus 1, but if I square this step, then it is simply equal to 1. So this means I get n ones, and this is how I get the answer, which is n again. Okay, so this is how you do it for the random walk. Now let's look at another martingale we know. Let's look at the Galton-Watson process. We know it will be a martingale if the offspring distribution has mean 1. So Galton-Watson process with mean a equal to 1, and I have to assume that it has finite variance, the offspring random variable, because we only talk about square integrable martingales here. So sigma squared, which is the variance of my offspring random variable, is finite. So I want to compute the quadratic variation of z at time n. I will use one of the two formulas here, and since there is nothing special about the increment of the Galton-Watson process, I'd rather use this formula here. So it will be the sum of the conditional expectation of zi squared given fi minus 1 minus zi minus 1 squared. Now, we assume that we know everything that happened before time I minus 1, and we can treat it as deterministic. So I will do the following to compute zi squared. I will say, okay, if I have zi minus 1 species in the previous generation, then I need that number of offspring random variables. So I will have n1 plus nzi minus 1. So if I sum them, this will give me the total number of children in generation I, and then I am asked to square it, take the conditional expectation, and subtract zi minus 1 squared. Now, I repeat, we treat zi minus 1 as a constant, and then here we are computing the second moment of this sum. What's the easiest way of doing it? Yeah, and so zi minus 1 goes as a constant through the conditional expectation, and otherwise these random variables are independent of fi minus 1, so I'm taking just the second moment of them. So I think I'm going to say that it is the variance of that sum plus the expectation of that sum squared, right? Why I want to do it? Because the variance of the sum of independent random variables is simply the sum of the variances. So I will have zi minus 1, the number of them, times the variance, which is sigma squared. And now I need to add the expectation of the sum, which is a1 multiplied by the number of them squared. And I have to subtract the last zi minus 1. And what we see happening is, I forgot the square in the last term. So what we see happening, we see that these terms cancel each other, and otherwise we see that it is sigma squared times the sum. I will let the sum run from 0 to n minus 1, and then I can simply write zi in this sum. So the sum of all individuals in all generations up to n minus 1 is the quadratic variation of the process z in at time n, multiplied by sigma squared. So when you have done the calculation, always check that what you obtained is growing and in particular non-negative. So this thing is clearly growing because when you add more terms, you only add new children, so you only make it bigger. So this is how it works for the Golden-Watson process. And the last example will be the Poe-Earn. So here we remember it is the proportion of red balls, Rn plus 1, in the urn. So here, again, there is nothing special about the increment of m. I will be using the last formula, the sum from 1 to n of the conditional expectation of mn squared given mi squared given fi minus 1 minus mi minus 1 squared So how do I compute the first conditional expectation? What is the expected value of mi squared? So with probability mi minus 1, here. So with probability mi minus 1, I will draw a red ball from the urn at time I, and with probability 1 minus mi minus 1, I'll draw a red ball at time I. Now, if I draw, with this probability, I draw a red ball at time I. With this probability, I draw a green ball at time I. Now, if I draw the red ball, then my mi becomes, so I can create it from this formula. So I'm thinking about it being for I rather than n. And then I add one ball and I increase the number of balls by 1. So this will give me ri minus 1 plus 2 divided by I plus 2 squared, right? What I have done just again, I have taken this expression, I have taken mi minus 1, and I looked at it and I saw what happened if another red ball was put into the urn at time I. Okay, now, if I put a green ball, which happens with this probability 1 minus mi minus 1, then it's simply that the numerator of my ratio will be by 1 less than this one here. So it will be ri minus 1 plus 1 squared. And I shouldn't forget to subtract mi minus 1 squared. Now, what I will do next, I want to have the final answer in terms of the process M, so I don't want to have any R's in here. What I will do, I will solve this with respect to R. So I will say that R at any time, and I will need it at time I minus 1, so let's do I minus 1, is equal to M at the same time, so I minus 1. Then it was n plus 2, so I minus 1 plus 2, I plus 1, minus 1. And I substitute this R I minus 1 into this formula. So into, more precisely, into here and into here. So this gives me a rather big expression with only one parameter, which is mi minus 1. So what I need to do, I need to simplify it, and I really don't want to do it now. I'm sure everyone is capable of just doing the cancellations, and there will be a lot of cancellations here. So I will just write down the term you end up with. It will be mi minus 1 multiplied by 1 minus mi minus 1 divided by I plus 2 squared, or if you like, you can write it as the sum from 0 to n minus 1, and then you can use mi 1 minus mi divided by I plus 3 squared. So this is the quadratic variation of the Poyer urn at time n. And again, the quick check, it is increasing because m, the proportion is between 0 and 1, so every term is now negative and adds to our quadratic variation.